This is graded assignment 3. So in this week, we have to incorporate Feast into the previous week's pipeline. So we have to set up feature store in Iris pipeline. The basic goal is to show how Feast acts as a bridge between a large offline data source, which here in this case is BigQuery, and a fast online store, and how it allows you to define and manage features as code. So let's go to the GCP. So in the previous week, uh, we created an iris data.csv where we had sepal width, petal width, and species. So the minimum requirement of Feast is that it requires two special columns to work, a unique ID for each row, which we will call iris ID, and a timestamp for which the feature was observed. So first, I have written all the commands over here. So first, we need to set the export the Google Cloud project ID. So here in my case, it is Velvety Rookery, as you can see over here. So first we will set up the Google Cloud project ID. So it is set, and we have to test that if it is set or not, then we will just run this command called Echo Cloud project. So it is showing that it is Velvety Rookery, this number. So we have set the Google Cloud project, and then we will prepare the feast data.csv. So I have written Python code to add the iris ID and event timestamp along with the data frame which I already have. Uh, so let's create that data. We will do Python prepare data.py. Yeah. So now, as you can see over here, we have got the iris ID and event timestamp with us. And then we will export this data set into the BigQuery database with the help of this command. So what this command does is it takes our local CSV and uploads it into the new BigQuery table called iris data. This table we will serve as our offline store, the single source of truth for all historical features data we have. So let's run this command. So it says that dataset iris feast dataset is successfully created. And then I have created featurestore.yaml. Here I have named the project and set the provider group, which is GCP. And most importantly, I've declared my offline store to BigQuery. This tells Feast where to look for historical data. And then coming to the iris features.py. So this file has three key parts. The first one being the data source. So it the BigQuery objects point directly to the BigQuery table we just created right now. This creates the link between Feast and our offline data. And the next component in this is the entity. An entity is the object our features describe. In our case, it is a single flower identified by the iris data. And then we have the feature views. This is the most powerful concept. A feature view groups related features together. I've created iris features for the measurement and iris target. Here you can see iris target for the species. Notice how they both use the same BigQuery source, which is iris BQ source. Here also, as you can see, this allows me to define my features once and reuse them everywhere. The schema explicitly defines the feature names and their data types, providing a strong contract for anyone using these features. Uh, After this, let's load this by running this command. So it says upload complete, and then the current status is done. After this, let's go to the feature repo file, and then do the feast applied. It will take a couple of seconds. So it says deploying infrastructure for Iris features and Iris target. So as you can see, we have got a new data folder over here, which stores the registry.db and online store.db. So this command reads my Python definition and saves them into the feast registry. If you look into the data directory, this created registry.db file. This is the feast internal catalog for all available features. We cannot view it. It it is not in the human readable form. So uh, this registry.db uh, is available for fast real-time lookups. We need to materialize them into the online store. So I will run feast materialize incremental with the help of this command. So this command reads the latest features value from our BigQuery table and loads them into our simple SQLite online store. This over here created the online store.db file. So we have now successfully used Feast to bridge the gap between our offline data warehouse and a low latency online store. So as you can see over here, both are showing 100%. And then uh, final step is we have to train the data. Okay, so let's move out of this folder, and then okay, so I have done some modifications in the previous week's train.py only. So the magic is in one of the lines, which is over here. Yeah, fs.get historical features. I simply tell Feast which features I need, and it handles all the complexity of going to the BigQuery and assembling the correct training data for me. My training code is now completely decoupled from the data source logic. So let's run this. Yeah, so it says connection successful, loading list entity list from the local prepared data, and it found 152 entities, and it is saying retrieving historical features from the BigQuery via Feast. So as you can see, the script connects to the feature store, retrieves the data from the BigQuery and successfully trains and evaluates the model. This demonstrates the power of a feature store in creating a clean, modular, and reusable machine learning pipeline. One more thing which we are missing over here is we need to check the BigQuery. So let's So over here, and over here in we can see feast. Yeah. So iris feast data set. Yeah. So iris data is over here. It takes a couple of seconds. Yeah. So as you can see over here, the iris ID, event timestamp, sepal length, sepal width, petal length, and petal width, species, all the columns are reflecting over here. We can go to the details of this big query and do a preview also. So as you can see, all the row ID, iris ID, and the event timestamp, which is the most crucial part for historical fetching the historical data. So all of this is coming over here. So that's all from this week's. Thank you.